First of all, I would like to thank the organizers for inviting me to give a talk at this remarkable conference on the great occasion. And on that occasion, I would like to wish a happy birthday to the algebra department of the Kyiv University. And of course, everything successful in research and in life to all the members of the Kyiv department. So I would like to speak on a joint work with Yves Cornelier from University of Lyon and Piotr Słanina, a colleague from my department. And I would like to speak about groups with a special kind of subsets and the consequences that containing such a subset on the group it has. So let's begin with a bunch of definitions, and we start with X being a metric space and a subset E of X, and we will call a point of the subset, let's say P, removable if both E and E with removed P are isometric. So it immediately follows that, of course, E is infinite, an infinite set. And okay, so the study of sets with removable points go back to works of Sierpiński and paradoxical decompositions that he studied. And he studied this concept of existence of sets with removable points in Euclidean spaces Rn. So it was followed also by Strauss and Michelski, and on the course of the work, the sets with removable points in Euclidean spaces could be like fall into three distinct classes. Not necessarily distinct, but on the course of the study, we could clearly see the three classes. So the first class is the sets with at most one removable point. And Sierpiński himself proved that in R, for example, every subset is of that type. On the other end, we have sets in which every point is removable. And somewhere in between, we have sets with few removable points, distinct removable points, and we stick with two. So since this was all motivated by Sierpiński's study, so we use the notation of Sierpiński sets for the sets of class 2, and since the third condition is weaker, we call weak Sierpiński sets that are the sets with two removable points. And later on, the ideas developed in this setting were transferred by Strauss to subsets of group. And of course, in order to consider subsets of kind Sierpiński or weak Sierpiński G, we have to assume that G is an infinite group. And we can consider the left action of the G on itself. That maps every element X of group to its left translation by G. And in this setting, we may look at the group and its Schreier graph related to some subgroup, for example, subgroup generated by G, and the left translations that will imply that will define isometries of the graph. So we can call a subset E of G a weak Sierpiński subset if there exist two distinct elements G and H in the group G, and two distinct elements A and B in the subset E. Of course, these are also group elements, such that G, by left translation, removes element A out of E, and H removes element B out of A, out of B. So in fact, in order to have a weak Sierpiński subset, we have to define the subset itself, of course, and 4 elements, GH, which define the action, and A and B, these are the removable points. Okay, so just to give you the idea how it works and how can be imagined, so let's consider a free group of rank 2 generated by the 2 pre-generators X and Y. So these are words, we can think of elements of this group as words in the 2 letters, of course reduced words, and take the subset of G, call it E, to be the set of all words with the last letter X, so ending with X. Obviously the empty word is not in there, so the identity of the group is not there, but X itself, a single letter, is contained in E, and also we have there the word YX. And now consider left translations of the set E. First, we translate it by X, and we observe that since identity is no in E, is not contained in E, then obviously X is not in this left translate by X. And similarly, YX is not contained in YX E. Therefore, we have exactly what we need for weak Sierpiński to be defined. We have a subset of the group, infinite subset, of course, such that we have 2 elements of the group, X and YX, that are removing from the set single points, singletons, like in X in the first case and YX in the second. So in this particular example, we have the case where A equals to G and B equals to H, but of course they do not have to be equal. So we see that for sure free group of rank 2 necessarily contains weak Sierpiński subset. And okay, let's first, before we move on to further characterization of groups with containing such subsets, let's give some basic observations. So assume we have a group with weak Sierpiński subset E, and the points that are removable are A and B, and they are removed by respective elements G and H. So the first observation is that since any left translate by of E by G is a proper subset of E, because we remove only one element when we left translate by G, and the same for H. Then obviously if we perform this iteratively, meaning that we left translate by some positive power of G or positive power of H, or a mixture of those, we only can decrease the set, so make it smaller, but we cannot get out of it. So it can be summarized that if omega is a semi-group word in G and H, then the left translate by the whole word, meaning that we iteratively perform this left translation by G or H, will never get us out of E. The second observation is that whenever we have weak Sierpiński subset in a group with removable points A and B, they are arbitrary, then you can easily define another weak Sierpiński subset, E prime, such that one of the removable points is the identity, the group identity. It is enough to right translate everything by A inverse in this case. So in the study of weak Sierpiński subsets of groups, we can always assume that that one of the removable points is the identity, which simplifies the description. Also, these group elements G and H, when we consider the subgroup generated by the 2 elements, let's call it H. If the subgroup is not free, then we may, based on E prime, so already the weak Sierpiński subset with the identity as one of the removable points, we may define weak Sierpiński subsets in H. It's just a simple intersection. So H also has this this kind of subset. And last but not least, necessarily both G and H are of infinite order, since if you assume otherwise, you will come to contradiction that sample point G to the power of M E should be equal to E, but it's not true, as every iteration of translating by G removes some point out of E. So both G and H have to have the infinite order. Okay, so in his study, Strauss in 1958 proved that the existence of Sierpiński subset in a group G. Sierpiński subset is the subset in which every point is removable. So if G has a Sierpiński subset, then it contains a free subgroup of rank 2. So in fact, it's equivalent. It's if and only if condition. So it's a natural question whether we can weaken the condition of possessing Sierpiński subset to just a weak Sierpiński subset. And this question was posed by Michalski, Tomkowicz, and Wagon in the work directly. They consider a little bit the question and conjectured the affirmative answer. What they proved in 2018 that if G contains a subset with 2 points removable by respective group elements G and H, so a weak Sierpiński subset, then G and H generate a free sub-semigroup in G. So in our work, we confirm that indeed the answer is yes. So we give a positive answer to this question, and we prove the following: that if G contains a weak Sierpiński set, then necessarily it contains also a free subgroup of rank 2. In fact, we observed that we can give quite short argument by using Stahling's splitting theorem that concerns ends of groups. So not to go into detail, you can think of ends like the ends of the calligraph, and each group either has one end or 1, 2, or infinitely many ends. A finitely generated infinite group. So Stahling's theorem, as a consequence, gives us the following condition for a group to have a free subgroup of rank 2. Namely, it has to have more than 2 ends. So in our case, if we have a weak Sierpiński subset in our group G, with these elements G and H that remove some points in our group, consider one of the removable points to be identity for simplicity. So it immediately follows that the subgroup generated by G and H also has the weak Sierpiński subset, so we can only work in this subgroup. And since necessarily weak Sierpiński subsets and its complement as well have to be infinite, so we have the observation that we have at least 2 ends. So it's only a matter to prove the theorem. Our theorem is we have to discuss the case of having 2 ends, but a group with 2 ends is always a virtually cyclic group, and if we consider this in a group in a subgroup H, we get a contradiction that G and H should be this one of the power of the other, which cannot be solved. So in this way we get that H has at least 3 ends, and this immediately follows that it contains at least subgroup of rank 2. Using this this tool, we also proved a little bit more in terms of what can be removed from the sets. So it's not only about singletons, like single points removed from the sets, but also any finite disjoint subsets. So if we assume that G removes from E a finite subset A, and H removes from E a finite subset B, and these subsets A and B are distinct, disjoint, then we also get the same result. Okay, but well, we actually studied a little bit more the subgroup generated by G and H and the structure of the free subgroup, because we know that the free subgroup exists. So let's try to figure out where to find it and how to find it. So what we already know from Michalski and Tomkovich's result, that G and H generate a free semigroup in G. But when you think about a free group, it's not the case. So the subgroup generated by G and H may be not free. And we can give a simple example for that. So if you take a free product of two cyclic groups, where one is of infinite order and the other is of order k, then when you take the subset E to be set of all reduced words in G and T ending with G, so a similar construction that I showed you for the free group of rank 2. And again, we see that left translates by G of the set removes G from the set, and left translate by TG removes TG from the set. So we indeed have a weak Sierpiński subset in the group G. However, G is not free. So so if this subgroup is not free itself, what is it? And this was our motivation for looking into details on the minimal relations that you can find on G and H that are satisfied in G. So what we proved is that up to cyclic shift, the minimal relation is of the form H G inverse to the power of k for some k at least equal to 2. And in this setting, when I'm only considering the case where in this the subset, the weak Sierpiński subset is defined with one removable point being equal to identity. So in this case, the other removable point is necessarily of the type Hg inverse to the power of m, for some m less than k. And putting that together, we can actually say more. It's not only the minimal relation, but it's the defining relation for that subgroup. So the theorem is as follows: if G contains a weak Sierpiński subset with 2 points, 1 and B, removable by the respective group elements G and H, and if the subgroup generated by these elements G and H is not free, then there exists an integer k at least equal to 2, such that H has the presentation with the two generators GH and only single relation H inverse G to the power of k. So we know the structure completely, as this subgroup is this kind of group is well studied. It's a free product of two cyclic groups, one of infinite order and the other of order k. So exactly what I showed you in the example. And if we want to look for free subgroups of in H, then it's enough to consider the subgroup generated by G and the conjugate of G by H. This also allowed us to consider possible weak Sierpiński subsets in G once we have the situation in a group, let's say subgroup generated by GH of the type of the presentation. So we show that there are exactly k-1 weak Sierpiński subsets in such group GK, so GK, with one of the removable points equal to the identity. So we give the exact characterization of those subsets. Let's call them EM. And they are defined in the Schreier graph by cutting along. So the idea about this weak Sierpiński subset is that it's a subset of group G, so it's a part of the, for example, Kelly graph, and it's the other part is the complement, and we have distinct edges that connect these two parts, and so we can define the subset EM in the Schreier graph by cutting along the edges G inverse 1, so G inverse identity, and the other one is related with this B element, which is necessarily of the type H G inverse to the power of n. So I know it's not a very clear statement. Just one more remark that then G left translate EM removes identity from the subset, and H removes the element Bm of the form Hg inverse to the power of n. And so to give you some picture of illustrating the last corollary, let's consider the Kelly graph of G3. So for k equal to 3. The Kelly graph is a net of hexagons in this case. In each of the edges is labeled by G or H, and we present here. So according to the corollary, we have the two possible weak Sierpiński subsets that's in which one of the removable points is the identity, and they are presented here on these two graphs. Of course, these are only parts of the whole infinite Kelly graphs. So it's the like first iteration. Let's say it's of a fractal type, and in the left you have the first possible situation when you the gray part is the complement of E, and the cutting edges are exactly the between the identity and the inverse, and the other is between the inverse and H the inverse. And in the other case, you have another choice of the two edges along you cut, but of course the first one is always the same, so you can only cut here. So we gave a complete description characterization of subgroups generated by the two elements that are responsible for removing points from weak Sierpiński subsets, and also described the possible weak Sierpiński subsets in such groups. So that's all I wanted to tell you today. If you are interested in details of the proofs, please refer to our archive version, or soon I hope it will appear in Fundamenta Mathematica as a whole manuscript. And thank you again for the possibility of having a talk here. It is very pleasure for me. Thank you.
Thank you, Professor Bier.